welcome back. And finally, after about a month and a half break, we're getting back into the vacuum tube computer. And I'm really excited about this because we're going to come up against some pretty complex topics that we're going to have to wrap our head around in order to get it to actually act like a computer. Now, the last episode of the vacuum tube computer series aired around, I think, the end of December. And between then and now, I believe that we've had a lot of new subscribers join the channel. In which case, thank you so much for joining and welcome. But also, if you're one of those new subscribers, you may be asking yourself, what on earth is this dude talking about? Well, about a year ago, I started a project where I wanted to build a homebrew computer out of vacuum tubes. But I wanted to use the vacuum tubes at extremely low voltage. So my B+ is just 24 volts, and I'm using negative 12 volts for grid biasing, which is a ludicrously low voltage for vacuum tubes. But the little 6AU6 is a trooper and it works beautifully at those low voltages. Now, I did take a look at some other designs, but ultimately I settled on the Motorola MC14500 as my main inspiration. And it has some quirky design features. As a result, we had to make a couple changes. Most notably, we changed the logic unit to a full-on arithmetic logic unit, so that way we can do proper addition and subtraction, but we remained within the 4-bit instruction limitation that it had. Now, this is a 1-bit processor. It does processing on only 1 bit at a time. So we have some interesting limitations that we're going to run into with memory. And speaking of memory, the processor doesn't have any memory on it. It just processes data, hence the name processor. So we actually got the processor working. We fired it up, put out a colossal amount of heat, but it all worked beautifully. But every time we did an operation, we had to write down the result because there was no memory. And so the total computer is going to be split into 4 different sections. There's going to be the processor, which we've finished and built. There's going to be memory, there's going to be program control, and there's going to be input and output. And so what I want to do today is I want to get started on memory. Now, a lot of people had some very excellent suggestions and ideas for how to tackle memory, but ultimately I ended up going with this design. This, I'm sure, looks very different to what everyone was hoping or expecting, but it's, I think, going to work really well for the strange limitations and requirements that we have. But before I get into exactly what this is and the design of it, I want to take a look at the other types of memory that I thought about going with. And I really want to take a look at how they work, maybe how I would have gone about implementing them, and ultimately why I didn't end up using them. So we're going to set this 1 bit aside for now, and we're just going to sit down at the bench and take a look, most notably, at Williams tube memory, at rotating drum memory, and finally at core memory. Core memory in particular is very interesting. I really want to do something with core memory in the future, but as we'll see, I just don't think it's going to work for this project. So let's hop over to the bench and take a look at these 3 types of memory and then see where we're going to go from there. All right, first things first, I'm a very hands-on type of learner. If I don't have the actual physical object in my hands so I can hook up probes to it and see how it works, I have a very hard time wrapping my head around, well, how it does what it does. And I don't have any of these types of memories at hand. I would absolutely love to. So if you happen to have a drum memory module just hanging about that you don't want, incredibly strange thing to ask. But if you happen to have one of those that you don't want, send me a message because I'm very interested it. But what that means is that everything that we're going to look at today is mostly just theory and kind of what I've taken educated guesses on based on the documentation that I've read. And so I could be totally off the mark on how some of these work. And if I am, please hop in the comments and let me know, because some of these, particularly Williams tube memory, the information on the ground is very thin. So if you have any kind of avenues into knowing more about these types of memories, definitely let me know, because I'm very interested in it. But let's go ahead and start with Williams tube memory. And this is a very fascinating type of memory because it uses a cathode ray tube. Now, it seems weird to use a cathode ray tube as a storage device because it's not. It's a display device. So how can you make a display device work as storage? And well, ultimately a cathode ray tube is very similar to a vacuum tube. You have a cathode that is emitting electrons, and those electrons are attracted towards an anode, which is held at extremely high voltages, usually 5,000 volts all the way up to 50,000 volts or more, depending on the type of CRT. And they strike the front of the tube where a phosphor is painted. And when the electron strikes the phosphor, at that specific point, the phosphor gets all excited and it starts to glow. But this idea of the electrons striking the phosphor is how we're gonna store data. When the electron strikes the phosphor, it causes it to illuminate. But if we crank up the power and we overdrive it a bit, when the electron strikes the phosphor, it's going to knock other electrons off. This is called secondary emission. So what this does is the point at which the electron is striking the phosphor is now becoming positive because it's knocking electrons off. And then those electrons get attracted back towards the phosphor, and it creates a charge well that is slightly positive in the center and slightly negative in a circle around it. And this turns out can be detected. So Williams tubes have an extra plate that sits right in front of the phosphor, right next to it, that can detect these charge wells. And so you scan left to right, top to bottom, creating a grid of dots, and that is your memory. Now, there is some weird control that has to go on in order to read those, and I didn't dig too deeply into this because, well, first of all, there's not a lot of information out there, and second of all, the entire vacuum tube computer is at 24 volts, and suddenly introducing 5 kilovolts so that we can run Williams tube memory kind of defeats the ethos of the vacuum tube computer, which is low voltage. And since you can't run a cathode ray tube at just 24 volts, well, Williams tube was out of the running right off the bat. But that doesn't mean that Williams tube memory isn't a fascinating piece of memory technology, and I absolutely would love to do something with Williams tube memory in the future. Maybe get my hand on an actual Williams tube, or even try to build one from scratch using an old oscilloscope CRT. But since we're not going to use Williams tube for the vacuum tube computer, we'll set it aside, and next let's take a look at rotating drum memory. Now, rotating drum memory is awesome because it looks like a portable nuclear reactor or something. I've never seen a drum memory module that didn't look amazing. But as insane as it looks, it's actually very similar to a modern day hard disk. You have a magnetic surface that spins, and then you have a read-write head that can read the data off of that. It's just that we're taking that disk and we're wrapping it around essentially a cylinder. And then we're spinning the cylinder, and instead of having the read-write heads fly across the cylinder, we have a bunch of them in a line across the entire drum, and they read or write as the drum spins past them. And the old vacuum tube computers used this type of memory a lot. The LGP30, the IBM 604, the IBM 650, most vacuum tube computers used rotating drum memory. Since the IBM 650 used a rotating drum, there's a lot of fantastic information about it in the customer engineering manual. And they have this wonderful little diagram here that shows how the data is split up on the drum itself. So one part of the drum is divided into 5 sectors. Each sector is divided into 10 word intervals. Each word is made up of 12 digits. And then finally, each digit time is divided into 4 equal intervals, A, B, C, and D. So that comes out to 50 words per revolution, which is a colossal amount of data being read very quickly. Well, how quickly? Well, in the case of the IBM 650, they spin the drum at 12,500 RPM. This is insane. This spins faster than most modern hard drives. And that is the primary reason why I started to veer away from rotating drum memory. Now, the drum doesn't have to spin at 12,000 RPM. I could spin it much slower, but that introduces other weird timing problems. I'm not sure exactly how fast you need to spin the drum in order for the read-write heads to work properly before you end up with weird issues with trying to read and write. Man, but I really do want to do something with rotating drum memory in the future. It seems like it's attainable, and it's definitely going to use different skills and abilities, and it would be a ton of fun to do something with one of these. But since we're not going to use it for the vacuum tube computer, we'll set it aside and we'll take a look at the most interesting memory on the table here, and that is core memory. And core memory kind of became the de facto standard memory until silicon memory started to take over. And actually, core memory was being used even on the first generation Centurion mini computers that were being built in the 1970s. And it works on the principle of essentially magnetization of an iron core. And so what this means is that if we run a magnetic field through a piece of iron, it will align the dipoles in there in a certain way that gives it a north and south pole. And then if we switch the magnetic field to the other direction, those dipoles flip and the north and south pole of that piece of iron flips as well. This is the primary concept behind core memory. So you have a toroid, which is just a little circular chunk of iron. You run a wire right through the middle of it. And when you put current through that wire, you can use the right hand rule. The direction that current is flowing is your thumb. That means that the magnetic field is going to go in a circle in the direction that your fingers curve. If we change the direction of current, my fingers are now curling in the opposite direction. That means the magnetic field is in the opposite direction, which means that the core is now going to have its dipoles arranged in a clockwise fashion. And so the magnetic core will keep the arrangement of its dipoles within it, which makes this non-volatile static RAM, because we can detect which direction those dipoles are in, and those directions don't change if we take the power away. Now, when we look at an actual magnetic core array, it's not just one wire. There's a bunch of wires going on here. But most importantly, we have X and Y wires because we want to create a grid, because we're just storing 1 bit or reading 1 bit. So we need to create a grid to access a single toroid, a single core. And this is where things get a little interesting, because now we have to talk about hysteresis. And this is the concept that it takes a certain amount of magnetic field strength for the core to flip. And this is the same in both directions. So we can have a grid where we have an X wire and a Y wire, and we can put half the amount of current that is required to get the core to flip on the X wire, and there can be a bunch of cores on that single X wire. And then we can put the other half of the amount of current that is required to get that core to flip on a single Y wire. And even though that entire row of X and the entire row of Y is receiving some current, it's only at the point that they intersect that the two magnetic fields combine, creating enough of a magnetic field strength to cause one core to flip. Now, this is excellent because it means that you can create huge grids of memory and select individual bits very easily. Except we can't really read the bit without destroying the data that's stored in it. It's called a destructive read. And the only way that we can actually read that bit is by causing the core to flip. So there is an additional wire that is woven through all of the cores that is called a sense wire. And whenever a core flips, it induces a little bit of current in that sense wire, and we can detect that blip of current as whether it was storing a 1 or a 0. Now, for example, if a core is storing a 1 and we want to see what that 1 is, we essentially run current in the reverse direction through that specific core, causing it to flip to 0. Now, when it flips to 0, it induces a spike of current. We detect that and we know that there was a 1 stored there. But stored is past tense because that bit is now storing a 0. So we have to rewrite that 1 back into that bit. Again, this is that destructive read problem. Now, if that core was already storing a 0, when we run current through it in the opposite direction, well, it's not going to flip because it's already in the state that we're trying to force it to be in, which means that the sense wire isn't going to detect anything, and the fact that the sense wire didn't detect anything tells us that a 0 was stored in there. But what this means is that we need some pretty complex control circuitry. So that means that we need quite a lot of pretty complex control on each individual X line and each individual Y line that allows us to send current in whichever direction we want it to be in, whether we're trying to write a 1 or whether we're trying to write a 0. And then it also means that we need a whole lot of circuitry to control what we do with what we detect from the sense wire. It means we need to, first of all, amplify what we detect from the sense wire. We need to store that bit somewhere in a register to say, hey, there was either a 0 or a 1 in there. And then if there was a 1, we need something to, again, select the same X and Y, only flip the direction the current is going in and write a 1 back into it. That is a lot of very complex control. The IBM 700 series computers had a core memory unit. But if we look at a picture of that unit, well, we can see that there's at least 200 vacuum tubes in use here. And that's just that part of the module. So if we were to try to use a core memory array, the control logic would be so large that it would be bigger than I have allocated room for. And that leads me to the biggest restriction that we're facing when we're talking about memory for the vacuum tube computer, and that is space restraints. The memory needs to fit within the same footprint as the processor, because the way I'm planning on arranging this is having each of the 4 parts be exactly identical in size, arranged on 2 racks right next to each other. My ultimate goal is to be able to follow a single bit throughout the entire computer. I want to be able to have this be a very visual thing. And core memory, first of all, doesn't lend itself very well to that, but also, even with a very small core memory array, I don't think we'd be able to fit it within the space that we've allotted for it. But this is not the last vacuum tube computer that I'm hoping to build. So in the future, I want to build another vacuum tube computer that maybe uses an 8-bit data bus, something a little more conventional with some core memory in it. But that's in the future. For this computer, we're not going to use that. We're actually going to use something that's much, much closer to a static RAM chip. But in order to figure out what I mean by that, you're going to have to hang around till the next episode. I am sorry that we didn't build anything in this episode, but I think it was important to take a look at core memory and why I don't think it'll work for us here. So I want to thank you guys so much for listening to me ramble about old memory. And I hope to see you in the next episode, because we're going to take a look at the actual memory that I'm planning on using, how I constructed it, how I came to that conclusion of the design that I'm using, and then ultimately the hurdles that we're going to have to tackle to actually build it. So I hope to see you then, but in the meantime, thank you so much.